Hi guys, today we're working on some applications of some quadratics, which are also known as parabolic functions. I did not make this worksheet first off. Found on the internet, wonderful worksheet. I do not know the original author, but I would 100% credit them if I did. You should have this, and if you don't, make sure you come get it from me. We're doing our notes on today. Alright, so using the graph to the right, it shows the height h in feet of a small rocket t seconds after it's launched. The path of the rocket is given by the equation, which says that the t is the time is the independent variable. The height is affected by the time because the further on it looks like it flies, the further it goes up until at some point it starts coming back down, which is how rockets behave. Bear in mind, this is not the path of the rocket. This is just how high it is, which is our height in feet, measured against the time in seconds. Okay, so how long is the rocket in the air? Well, look at the graph. 8 seconds is what it looks like. So we're going to put 8 seconds. What's the greatest height? Well, if the y-axis measures the height, then our greatest height is going to be at, right this point, it looks like we're at 260 feet. How high is the rocket after 1 second? Let's see, we'll go over to 1 second. We'll go up to the height. It's like we've got 110 feet is our height here. After 2 seconds, about how high is the rocket? So it looks like this rocket keeps going up. After 1 second, it's at 110 feet. At 2 seconds, it looks like it's at, well, it's kind of hard to tell. They've got this dot here, which is a point, but I'm going to go with 200 feet because I feel like this line crosses exactly this 2 x-axis and our input at exactly at 200 feet. And is the rocket going up or down? Well, it looks like right now it's getting higher and higher and higher and higher, so I'm going to say going up.
It looks like the rocket is about how high, so we're going to go over 6 seconds here. It's about the same height, maybe a little bit lower. So maybe I can see 190 feet here. Is the rocket going up or is it going down? Okay, so it looks like we're going up, 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 and then coming back down, so we're going to say down. Do you think the rocket is traveling faster from 0 seconds to 1 second, from here to here? That's how much distance we cover is going up 100 and something feet, or from 3 seconds to 4 seconds, which is going up from here to here, which is only about maybe 20 feet? So if I'm asked the question of which of them travels further, 100 and something feet or 20 something feet, I think that I know which one travels further. And it travels it in the same 1 second interval. So if we're traveling farther in the same time interval, that says that one of them is definitely going faster, which is the 0 to 1 second. We went much further in that distance than we did in the 3 to 4 second interval. So traveling faster from 0 to 1 second because the rockets went further in that time. Using the equation, find the exact value of the height at 2 seconds. So if we use our equation, which is h equals negative 16t squared plus 128t, and we want to know exactly 2 seconds, well, our t is our time, which says that we're going to use that for t, so it's like we're going to have h is going to equal negative 16 times 2 squared plus 128 times 2, which is going to give us negative 16 times 4, exponents first, remember, before we multiply, plus 256. Multiply first, so we're going to get h is negative 64 plus 256, which is going to give us a total height. Do this in your calculator, please. I'm going to do this in my calculator, so I'll make a mistake here. So 256 and minus 64 gives us 192 feet, which says that when we had about 2 seconds, we guess at about 200 feet, but it looks like that our equation may be more modeled at exactly at around 190. So looks like that to find our exact height, we're definitely going to have to plug into the equation. You can kind of guesstimate from a graph, but we can't get it exactly. Alright, what's the domain of this graph? So the domain refers to all the x values, all of our input values.
looks like this rocket goes up and comes back down. It didn't start before, and it doesn't keep going afterwards. So we can say our domain is from 0 is less than or equal, so that's our starting, which is less than our time involved, t is our variable, which is less than or equal to 8, because that's where the rocket stops. So start, which is less than or equal to, this is a solid circle, our time, which is our x-axis variable, which is less than or equal to, stops at 8. What's the range? Well, it looks like the lowest height we have is 0, and then it goes up, goes up, goes up, goes up to, what do we say, 260, which we might need to plug that in to find the exact value, but for the range, let's just guess right now and say about 260. That's what we said our maximum height was. So 0 is less than or equal to our height, which is less than or equal to 260. 0 feet, which is less than or equal to all the height we covered, all the way up to about 260. Express the interval over which the graph is increasing. So when we have increasing versus decreasing, that's pretty self-explanatory. Is it going up or is it coming back down? So when we're looking about the interval over which the graph is increasing, we're looking at the domain. So the domain that is increasing looks like our vertex is at 4, which says that's our highest point, which says that everything before that is increasing. So 0 is less than or equal to t, is less than or equal to 4. It's actually not equal. Looks like it's just kind of hanging there.
We're not going up, we're not coming back down. And then the last question, express the interval over which the graph is decreasing. Looks like we're going from 4 all the way down to 8. So 4 is less than or equal to t, which is less than or equal to 8. And again, I should not have put that equal to for that 4. So we should have 4 is less than t is less than or equal to 8, because at that 4 it's just kind of hanging there. If you've ever thrown a ball up in the air, when you're at the very, very top of it, if you were to slow that time down enough, you would see that ball is not moving. It's just kind of hanging for that split second in the air, which is why we're not really equal to. But I'm not going to be a stickler about that. This is more my college physics talking than my math talking right now. Alright guys, that's the ending example 1.